If you subject a fluid to a sudden change in pressure, some interesting things can happen. You can cause tremendous damage to moving parts, but you can also harness that destructive power for many beneficial uses. From mana shrimp killing their prey to ultrasonic cleaning, so many things rely on this fluid phenomenon. Hey, I'm Grady, and this is Practical Engineering. On today's episode, we're talking about fluid cavitation. This episode is sponsored by Blue Apron. More on that later. You might even call this video a treat especial because it's the story of what may be one of the most inept YouTube collaborations of all time, thanks to me. It all started with a sketch of a venturi. A venturi is a device that constricts the flow of fluid to take advantage of Bernoulli's principle. You may have heard of this principle, which basically says that all energy in a fluid can take one of three forms: kinetic, potential, or internal energy. And the total amount of energy is the same along a streamline. So if you change one, for example, if you increase the kinetic energy of a fluid by speeding it up, you have to accommodate. In this example, the fluid's pressure goes down. Being able to lower the pressure of a fluid or create a vacuum just by constricting the flow area makes a venturi a very useful tool that can be found in all kinds of devices, from engines to trombones to scuba diving regulators. So I thought I'd like to have one of these venturis, and I know just the guy to make it for me. You may have heard of his YouTube channel, Arduino vs. Evil, now cryptically shortened just to AvE. We've never seen his face, but we're pretty sure he's handsome. Him and I had been emailing ideas across the US-Canadian border, and this seemed perfect. I have a channel centered around practical demonstrations of engineering principles. He has a clapped-out Bridgeport milling machine. It was a match made in YouTube heaven. So I sent the sketch over to AvE and said, "Could you make something like this?" And he said,
"The drawings are never right. There's details left off. The guy doesn't know from his elbow, or whether it's drill pressed punched or bored."
But he tried to make it anyway, providing us with many excellent lessons about manual machining.
Just busted out. So there's three ways to do this: the dirty way, the hard way.
And in a second video, the prototype was finished, and we were left with these parting words.
If I were a betting man, and I am, I'd bet that this ain't gonna work.
And it didn't. Or at least, I have to assume it didn't, because 10 months later, I got this in the mail. Instead of giving me the hard truth that my sketch was poorly considered and I wasted his weekend, he gave me something even better. A care package including a clear acrylic liquid flow meter that was designed by someone who knew what they were doing. And if you look closely at this flow meter, you might recognize the shape as a venturi, which is perfect because I need a venturi to show you this fluid phenomenon. Here's my setup. I have my garden hose running into the garage and a pressure boost pump feeding a manifold that connects to a pressure tank, a pressure gauge, and this flow meter. I modified the meter so it acts like a venturi by gluing the weight to the center post so it can't slide up and down. And I have a differential pressure gauge to measure the pressure drop across the venturi. The drop in pressure is the whole purpose of this demonstration. To understand why, we need to look at the phase diagram of water. We know that water changes state based on temperature. It's a solid when it's cold, aka ice, a liquid at room temperature, and a gas when it's hot, aka steam. But the phase of any substance also depends on the ambient pressure. You can see that even at room temperature, water can turn to steam at very low pressures. This is true for a lot of substances. If I force this water through a small enough opening in the venturi, according to Bernoulli, I'm decreasing the pressure and converting it to kinetic energy. And if I get the flow going extremely fast, I can decrease the pressure below the vapor pressure of the water, converting it to steam. Steam on its own isn't that big of a problem, but the issue comes on the other side of the venturi, when the pressure goes back up above the vapor pressure and the steam collapses back into water. On a larger scale, this collapse can lead to thermal shock. Check out my video on steam hammer to learn more. But on a smaller scale, collapsing steam bubbles are called cavitation. And even though the scale is smaller, the damage cavitation can cause can be just as destructive. This is because collapsing steam causes water to accelerate and decelerate violently. Water isn't compressible, so it slams into itself, creating a shock wave. It's like 1,000 tiny water hammers. In many cases where cavitation is occurring, you can even hear these shock waves, which sound like gravel moving through a pipe. If I build up enough pressure in this tank and open the valve to the venturi, you can clearly see and hear the cavitation occurring. I can't measure the pressure at the constriction of the venturi, which will be a very strong vacuum, but this gauge measures the total loss in pressure caused by the turbulence and cavitation, just for reference and because it looks cool. Needless to say, in many cases cavitation can be bad news. It can erode pipes, impellers, and other moving parts, leading to accelerated wear or even catastrophic failure. So engineers generally avoid designs that might subject liquids to sudden changes in pressure. Pipes get smooth bends rather than abrupt changes in size or direction. Boat propellers and pump impellers are carefully designed to match with the speed and power of the motor to which they're attached. And dam spillways are designed to avoid any protrusions into the high-velocity flow. However, although it's generally avoided in all kinds of industries, cavitation can be a force for good. Ultrasonic cleaners use cavitation to agitate a solvent and break the strong bonds between a contaminant and a part. Some industries use cavitation to mix compounds that are difficult to combine, like paints. Finally, some shrimp can move so quickly they create a cavitation bubble to kill their prey. As for this flow meter, it seems to be holding up fairly well so far. The acrylic seems to be able to absorb the shockwaves better than metal would. So it's probably best that our collaboration worked out the way it did. Thanks to AvE for supplying the demonstration for this video. If you like seeing the insides of tools and industrial machinery, check out his channel and tell him I sent you. Also, thank you for watching, and let me know what you think. Thanks to Blue Apron for sponsoring this video. Blue Apron delivers all the fresh ingredients you need right to your doorstep in exactly the right proportions to create delicious recipes at home. I cook about as well as can be expected for a civil engineer, but even I can follow these instructions. These meals are some of the best I've ever had, and we really enjoy cooking them together. If that sounds like something you'd like to try, the first 100 people to click the link in the description will get $50 off your first 2 weeks of Blue Apron. Again, thank you for watching, and let me know what you think.